Hi, everybody. Today we're starting, or this video, we begin chapter 11. Now, some of you are saying, wait a second, we were just on chapter like 2 or something. Like, how did we get to chapter 11? What happened to all the other chapters? Well, this book has a lot of material, a lot of chapters, and it's not possible to do all that has to be the entire book. And that's not the point of this class. The point of this class, as I've said numerous times, is not the what, but it's the how and the why, and just understanding some of the ways of math. I don't know how to say it better than that. So we're going to do chapter 11 about algebraic structures. And one of the very basic, famous algebraic structures is something called a group. So let's get to that right now. A group. So what is a group? It's funny you should mention. A group. Where is it? I'm gonna have to get rid of my beautiful picture because it's hard to explain, but it gets in the way. Okay, so groups. The definition of a group consists of a non-empty set G and a binary operation. Binary is that it takes two elements on G, satisfying the property. So now a binary element, a binary operation, if you will, is you can think of it as it takes two elements and assigns to that a different element. An example of a binary operation, regular number, just addition. 3 plus 5, that the plus is a binary operation, so that gives me a new number. In this case, it gives me 8. How do I know that? Because that's how many fingers I have. I can count, fingers. So a group consists of a non-empty set G and a binary operation star or whatever on G, satisfying the properties that the star operation is associative on G, and meaning that A star B star C is equal to A star B star C, meaning that it's ABC, ABC, star, 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 star. The difference is the parentheses. That's the associative operation. That's something that works, as you know, in regular numbers and so forth. So that's the first condition. The second condition is that there has to be what's called an identity element. Now, with let's say integers and addition, the identity element is 0. With multiplication, the identity element is 1. A group is going to have whatever identity element, different groups have different identity elements. And finally, for all A and G, for any element of G, there has to exist an inverse. That is, there exists a B also in G, such that A star B is equal to B star A, which is equal to E. I don't know why, for some reason in group theory, whenever they use E to represent the identity element, instead of using I, they use E. So that represents identity. So an example, 3 plus negative 3 equals negative 3 plus 3 equals the identity element, which happens to be 0. The identity element of addition is 0. Okay. A group is usually denoted by the set's name, but sometimes we'll write it this way. G will mention what the operation is. That's true. It makes a difference. So Z, which is the shorthand for the integers. Sometimes you can write Z. You can write Z plus, Z comma plus, because that's we're talking about the integers under the operation of addition. And the inverse is inverses we're going to see, here are unique. So therefore, the identity. So therefore, I could write negative n as the additive inverse of n, and so forth. Let's give some examples. Okay. The integers with addition is a group because we know that we know it's associative. We've seen that in elementary school. We know that 0 is the identity element for addition because 0 plus n equals n plus 0, which just equals n. And the additive inverse is just negative n. So the additive inverse of n is just negative n. Now the integers with multiplication is not a group, because multiplication, yes, is associative, and yes, it has an identity element, but it doesn't have inverses, because the inverse of the multiplicative inverse of 10 is 1/10, and 1/10 is not an integer. Now, if you want to talk about rational numbers, that's another story, but integers is not a group. The power set of any set U with the operation of symmetric difference is a group. So if A and B are sets, then A symmetric B, which is equal to A union B minus A intersect B, that forms a group. So if I take P of U, which is a power set of some set U, and the operation I'm using is a symmetric difference operation, then which is the union minus the intersection, then now we would need you to prove. Now we need to prove that it is associative, but what's it? We'll do that. We'll do that in a few minutes. But first, what is the identity of the group? Well, the identity is just the empty set, because A union the empty set, that's just A. A intersect the empty set, that's empty. So it's A minus the empty set. Well, A minus the empty set is just A. So we see that the empty set is an identity element. And what would be the inverse of A? Well, the inverse of A, believe it or not, is the set itself. Because A symmetric A, well, that'll be A union A, which is A, minus A intersect A, which is also A. A minus A is the empty set. So A itself is its own inverse, and the identity element is the empty set. And that's pretty awesome. So so the power set, and again, what's the power set? The power set is the set of all subsets. Power set, just in case, just to be clear, let me put that actually. I'm gonna put that into. I'm gonna type that into the text actually. Let's see. So P of U, the power set of U is the set of all subsets of U. There you go. So I'm just giving that definition. We've done this, but I just want to just have it here. Okay, so that's a good thing. And let's we just save that. And how we're done, we're gonna save it. Yes. Okay. We're good. Alrighty. So that's the story with that. Now how do you show that this is associative? How do you show this is associative? So let's go look at that. How do we show that symmetric difference is associative? And I'm gonna take this here. I'm gonna copy this whole thing. And I'm gonna paste it. I'm gonna paste this into our let's do this is better. Much better. All right, so let's copy this now. Copy. And I'm gonna put this into our chapter 11. All right, so I want to show how it's associative. So let's work on that. Now, to show that the associative property, well, the easiest way to show it is with Venn diagram. So here we have A union B minus A. Now I don't know how to do shading on this. So I just labeled the regions. So A union B minus A intersect B union with C. Well, A union B minus A intersect B, which is that symmetric difference, is going to be 1, 4, and 3, 6. When I union that with C, I basically want to getting everything except for 2. I get 1, 3, 4, 6, and I get 7. So I get 1, 3, 4, 1, 3, 4. Oh, I forgot the 5. I get 1, 3, 4, 5, 6, 7. I get all that stuff. When I do A union B minus A intersect B and then intersect that with C, I just get this little region down here, 4, 5, and 6. Now when I subtract, if I have the regions 1, 3, 4, 5, 6, 7, and I'm taking away 4, 5, 6, I'm just going to be left with 1, 3, 7. So so basically A union B minus A intersect B union C minus A union B minus A intersect B intersect C is equal to 1, 3, 7. Okay, that's so again, this is symmetric difference of A and B, and now when I introduce the C, it's symmetric difference of A and B, symmetric C. So the next thing you have to do is look at A union B union C minus B intersect C minus A intersect B union C minus B intersect C. That's the other. And you have to show that equals 1, 3, 7. You're going to use the same argument. Now, if I give you this question on a test, you can't just write by the same argument. You have to actually show me how the Venn diagram. You have to draw out the Venn diagrams for me. But that's that, my friend, is the story, and that is why it is indeed associative operation, and it is indeed a group. And that concludes. Does that conclude, or maybe there's one more? There's one more thing I wanted to just mention. That's this idea of modular arithmetic. And you've probably seen, many of you have probably seen this, but that's it. And like, for example, mod 7. Mod 7 is the numbers 0, 1, 2, 3, 4, 5, 6, or from 0 through 6, which is the possible remainders if an integer is divided by 7. If I take any integer divided by 7, the remainder is either going to be 0, 1, 2, 3, 1, 2, 3, 4, 5, or 6. Well, if I look at this, I can add these numbers and I can multiply these numbers. In other words, if I'm for example, 4 plus 5 in the world of mod in the world of mod 7, well, that's equal to 9. That's equal to 9. Mod 7. The only thing is 9 mod 7, well, is equivalent to 2 mod 7. And the reason is because if I would take 9 divided by 7, I'd get a remainder of 2. So that's what we're looking at here. And I could also do multiplication. 4 times 5 in mod 7 is, well, that's equal to 20 mod 7. But 20 mod 7 is the same thing as 6 mod 7. And that's how that works. Now, I may be interested, maybe if I take 0 through 6, and I use the operation of multiplication, maybe I'll have maybe it'll form a group. If I take these numbers or some subset of them, I might take 0 through 6. I might take 1 through 6. I might take whatever 3, 4, and 5 only. I could take whichever numbers I want, and see if those numbers form a group under multiplication or under addition or whatever, and which means, do they satisfy the definitions of a group? So this is just some information. This might be relevant on the test. That's a big hint. It'll definitely be relevant on the test. This might be relevant on the test. And that is the story. So everyone, it's been wonderful, and we'll see you next time. Bye.